All right, welcome back. Hopefully everybody's ready for some chemistry. Chemistry, yay. Oh, all right, you can save the cheering for later. So, last week we did chapter 5. Now we're on chapter 3. So for the test on October 27th, there's going to be chapter 9, 10, the one we're about to do, and then 5. So 9 and 10 were Lewis dot structures, Vesper. Chapter 5 was all the gas laws. And we're about to do molecules, compounds, chemical equations, balancing equations, naming compounds. So it's kind of a mishmash on this next test. Okay. Oh, mastering due tonight and Friday covers chapter 5. So since we did chapter 5 last week, I saw some of you guys have already done the homework for this week, so that's awesome. And we'll do a group quiz on Friday on chapter 5 material. So, good? All right. We're in the downhill part of the class. We're already halfway done, which is crazy. Crazy, I know. How many weeks do we have left? We have 1, 2, 3, 4. Only 7 weeks left. Yeah, exactly halfway. Very good. All right, so molecules, compounds, and chemical equations. So using kind of an easy example. All right, so hydrogen, oxygen, and water. Hydrogen by itself is an explosive gas, right? H2 gas. Oxygen is a gas needed for burning, right? Oxygen. But water is a very different molecule than either of these, yet contains both the hydrogen and the oxygen. We'll say water is a gas. So remembering our definitions from chapter 1. We talked about compounds versus mixtures. So a compound is an element or elements All right, so compounds were those things that are combined together in fixed definite proportions. What was the law that told us about that? Law of definite proportions. That's right, law of definite proportions. It's in there. So compounds are ruled by the law of definite proportions, that water is always 2 H's to 1 O all the time. A mixture is where you have 2 compounds together in a variety of ratios. All right, so a mixture says, like you have oil and water, or you have water and sand. Like you have 2 things that are by themselves individual compounds, but then you can mix them together in different ratios to get different combinations of mixtures. So the question is, how do you know what kind of compound you have made? What is the definite proportion? And then what do you name the thing that you've made? Welcome to chapter 3. We'll answer all those questions. Yay! I know, it's inspiring, really. All right. Here's my picture in case my words have been confusing. All right, hydrogen and oxygen are 2 compounds that can combine together in any ratio. But water is always 2 hydrogens to 1 oxygen all the time, every time. So mixtures versus compounds. I accidentally double-sided my slides, and I don't like it. I'll have to figure out how to fix that next time. All right, so let's review chemical bonding. All right, so chemical bonds are those things that hold atoms together and a result of the interactions of the electrons. Which electrons, the core or the valence? Right, specifically the valence electrons. So the valence electrons of the atoms are available to bond. And there's two types of bonds. What are the two big categories of bonds we have? Covalent is one of them. And the other one's a bond that's not a bond. Under covalent, what was the subcategory? Hydrogen bonding, or there's hydrogen bonding fits into a bigger category. Starts with a P. So under covalent, you can have a polar bond or a non-polar bond, or you can have ionic bonds, which are different. All right, so your covalent bond is when you have two nonmetals. They hung up my periodic table. I'm very excited. Two nonmetals sharing valence electrons. It's like a carbon-oxygen bond, or a sulfur-nitrogen bond, or a phosphorus-sulfur bond, something crazy like that. If it is a polar bond, how's that sharing done? Evenly or unevenly? Okay, so we have uneven sharing. And what is a polar bond? Like, how do you know if it's polar? What do you base your prediction on? Electronegativity, yeah. I really thought I would have shaken this cold by now. All right, so nonpolar would be even sharing. I guess this parentheses is true for both. Both are based on electronegativity changes. All right, or if I have an ionic bond, we'll have one nonmetal with one metal. So a sodium chlorine or a calcium bromine, something like that. An ionic bond, why do I call it not a bond? It's a transfer of electrons, right? Really. Who, the metal or the nonmetal, is more likely to donate its electron? So metals are the ones on the far left, and nonmetals are the ones on the right. So who's going to give away their electrons? The metals, right? And if they give it away, are they a cation or an anion? Yep. All right, so let's talk about ionic bonds a little bit more. So, there we go. All right, so since metals tend to lose their electrons and nonmetals tend to gain them, we often see an ionic bond when a metal and a nonmetal react. Oh, let me find my, here we go. So let's say I have sodium chloride. Which one of those two is the metal? Right, the sodium's the metal. So what's chlorine? The nonmetal. So based on what we know about metals, nonmetals, as well as Lewis dot structures, as well as electronegativity, what should be the charge on the sodium? +1. All right, so sodium normally has 11 electrons, but it's more than happy to give away an electron to only have 10 electrons, what would be the quantum numbers of the electron that it gave away? Quantum number. 3s1, right? It gave away its 3s1 to have a full 2p6. Okay, good. Okay, what about chlorine? What charge should chlorine have then? -1, right? And they're stuck together like that. Okay, what about we had, let's do another one. Let's do it in reverse. All right, so I have magnesium as number 12. How many electrons does magnesium want to give away? 2. So what charge should I give magnesium? +2. What about bromine? What charge should bromine have if it's an ion? Okay. So then I have magnesium is +2 and bromine is -1. How many bromines do I need to make this compound? How do I show you that I need 2? I see all kinds of crazy things on tests. I've seen all of these varieties, only one of which is really good. What is this one telling you? Really, I mean, nothing useful, no. It's equally weird. Right, the little 2 says double the thing it's touching. The big 2 in the middle is also odd. It's weird. All right, this is the right one. This one tells you I want 2 bromines. Why is there not a number 1? It's implied, right? It's not incorrect if you wanted to write this. But it's just implied. If there's no number, it's as though you're saying the number 1. Okay. All right, so those are ionic bonds. And again, another picture, very exciting. So here I have sodium becoming a sodium ion, chlorine becoming a chlorine ion. Normally, sodium's a metal and chlorine's a gas, but when it comes together, it's a delicious crystalline lattice structure that you put on food. Anyways. Let's look at covalent bonds. All right, so these are non-metal bonds where we have electrons shared. Let's say we have CH4. First thing I want to do is I want to draw the Lewis dot structure for this. So do I put the C or the H in the center of my molecule? C. How do I know that? It's the least electronegative plus hydrogen always has to be on the outside. So, all right. How many valence electrons does carbon normally bring with it? 4. So then, right, I can put my hydrogens in. So how many covalent bonds have I made? 4, right? 4 covalent bonds where the electrons are all shared. Are there any lone pairs? No. So what Vesper structure should this have? It is tetrahedral. Excellent. So it should really look like... like you did in lab last week. It's not pretty. Something like that. Oh, should I have a follow-up question? Oh, is this molecule going to be polar or nonpolar? Nonpolar. Why is that? Right? All of these bonds have the same amount of electronegativity difference, so they're all going to cancel each other out. Okay, good. Let's do another. How about... right, so if I have SO2, what goes in the center, the S or the O? The S, okay. Okay, what do I need to do to finish off that structure? I'll put some double bonds in. All right, so does the central atom have any lone pairs? No. So what Vesper structure would you call this? Linear. So pretty much as drawn. Is it polar or nonpolar? Nonpolar. Are the bonds polar? Is this a polar bond? Yes, it is a polar bond, right? Because they don't have the same electronegativity, right? O is going to be more electronegative than S. So this is a polar bond, but overall the whole thing is nonpolar. So this would have been an excellent example if you had chosen this on your quiz last Friday. That would have been genius, and some of you guys did. Good. So that was a polar bond, but overall the whole thing is nonpolar. So, just saying, when you get your quiz back and you look at it, you're like, oh, that would have been good. All right, so then, that's all a good review. All right, so chemical formulas. Chemical formulas, which is what we've been drawing, we just haven't been calling them that, indicate the number of elements present with the relative numbers of atoms or ions in each. We can write a formula in 3 different ways that gives the same amount of information, just presented in 3 different ways. All right, so the first one, you can't see my numbers very well. 1, 2. All right, so an empirical formula gives the relative numbers of atoms of each element in a molecule. So that's what we've been using. We've been using the empirical formula. Oh, sorry. We've been using the molecular formula. Empirical. Let's see if I can do it. I'll go through the definitions, then I'll give examples. It'll make more sense. All right, molecular gives the actual numbers, and structural shows it as a picture. So if I want to look at all right, hydrogen peroxide. This would be the molecular formula, because I've shown you I need 2 H's and 2 O's to make hydrogen peroxide. Empirical formula is where you use the lowest common denominator and divide everybody by that. So in this case, right, they both have 2, which means it's the same ratio as 1 to 1. So the empirical formula just says there is a basic ratio of 1 to 1. It doesn't tell you, it could be like 4 to 4, it could be 6 to 6. All you know is that there's 1 H for every 1 O. And then the structural formula tells you what it looks like. Let's see. So that's your Lewis dot structure, to be the structural formula. It tells you how physically they are connected together.
What if you had like just like H5O2? Like how would you call it?
Then the molecular and empirical would be the same. Right, because they don't have a common denominator. So if I had, let's see if I can come up with something. All right, I have H2PO4 minus. Can I divide this by anything to end up with a whole number still? Not really, right? Because I have one P. And so even though the 2 and the 4, I could cancel it, I only have one P, which means that this is both it's both the molecular and the empirical. So I can't make it any smaller. But what if I had, let's see, what would be? If I had C6H12O6 as my molecular, what would be its empirical? Mm-hmm. So they tell you the same information, just the molecular gives you the exact ratio, and the empirical gives you the lowest common denominator ratio.
So those subscripts have to be even?
They have to be whole numbers. Whole numbers. Like I could have, let's make up a compound. All right, I have C15H45. You can't, but you could. Let's say in my imaginary chemistry world. So those aren't even, but then it would be CH3. Right, so. It's not a real compound. That can't exist. All right, good so far on those definitions? Okay. So let's talk about what's going on the atomic level. All right, so atomic elements are those that exist in nature using a single atom of an element. So we've talked about this a little bit before, but just as a review. So these would be all of the noble gases. They exist as single elements. Or some of the metals, you could have just nickel or iron. Right, those are all elements that are not compounds. They're just single elements that exist in nature as a single compound, or single element. Molecular elements exist as 2 or more atoms in a basic unit. So these are elements that are always found at least in a pair. So this is, right, oxygen, nitrogen. Then there's some wacky ones. Phosphorus likes to have 4. Sulfur likes to go around in sets of 8. Why not? So these are elements, right? They're just all the same thing, like 2 oxygens or 4 phosphorus all linked together. But they're molecular because it has more than one atom in its compound. So then we can take these elements and combine them together to make either the molecular compound or ionic compounds. So molecular compounds have 2 or more elements that are different, I guess. 2 more. Right, because if it was the same element, it'd be a molecular element. So that'd be 2 different elements. So these are all the things we've been looking at, molecular compounds, right? Water, CH4. So they're all nonmetals. So if they are molecular compounds, what sort of bonds should they have? Covalent, right? Molecular compounds specifically have covalent bonds. All right, so the ionic compounds must have ionic bonds. These are like the ones we were looking at a few minutes ago. KBr. Something like that. Where it's a non-metal and a metal found together, but it's not a covalent bond. One has transferred the electron to the other.
Do you ever have both bonds in the compound?
Say that again.
Do you ever have both a covalent and ionic bond in the compound?
Yes. So like when we have, happens a lot in biology and biochemistry, where you have a long chain carbon, but the head group is like an NH3 plus or an H4 plus, and then it grabs onto a fluorine, so it has both polar and nonpolar and ionic bonds all together. So, all right, so that should be all review. All right, good warm up. Let's talk about then how we name them. Because up till now, it's been cool if we just said KBr or CH4 or NH3. Now we're at the point where we can use our proper naming skills. All right, so ionic compounds always have an overall charge of 0. And many elements, like we've talked about, right? Everybody in that first column, lithium, sodium, potassium, rubidium, cesium, francium, always are +1s. You move over 1. Those guys are always +2s. You scoot over to the other side of the table, right? Fluorines, bromines, always -1s. Always -2s if you move in 1 more. So since they have a predictable charge, we can predictably put them together and come up with snazzy names for them. All right, you ready for some naming rules? I bet you are. Okay. All right, we'll start off with naming cations. All right, so for a metal cation, which would be all of our sodiums, magnesiums, calciums, potassiums, strontiums, rubidiums, franciums, those guys. You're going to name the metal and then put the word cation after it. All right, real tricky so far. So if I have this guy, Mg2+, I would call it magnesium cation. We're going to do the easy naming first. The molecular ones are trickier. These guys are pretty straightforward. What if I had this element? What would I call that guy? Sodium cation. That one's pretty self-explanatory. All right, so for the transition metals, which is everybody in that kind of center part of the table, those guys can form more than one version of a cation. So you're going to indicate to the reader which one you're talking about using Roman numerals. So iron's a good example. It can form two different cations. It can form at +2 or +3. So to the reader, if you're going to write this out in words, we would call this first one iron. In the parentheses, you tell me it's Roman numeral 2, which tells me it's a +2 charge. Then the word cation. If I had this one, how many I's do I put in now? 3. So, right, this is pretty obvious when we're using chemical symbols. In words, you have to tell me, is it the +2 version or the +3 version? Everybody remember the Roman numerals, at least up to 10? Okay. All right, so let's name some anions then. These are a little trickier, a little bit. Okay, so a negative ion is monatomic, meaning just one atom. You're going to add the suffix "ide." Does suffix go at the beginning of the word or at the end of the word? And a little bit of English practice too. Prefixes and suffixes. Okay, so let's say I have F minus. You're going to tell me, the reader, that this is fluoride. All right, so it was, if it's regular F, it was fluorine, but now it's fluoride because it's a -1. So we go from fluorine to fluoride. We can also do all right, so it was, if it was regular P, it would be phosphorus. I can never spell phosphorus. O-S-P-H-O-R-U-S. All right, so it was phosphorus. It is now phosphide. All right, second part of naming anions. Put it over here. All right, so polyatomic anions are super common. So if it's polyatomic, how many atoms does it have? More than one, right? So this was single ones. This means that these are anions that have more than one element in them. So there are some guidelines, but in general, there is a great table in your book. In your book, table 3.1. Those are all the anions that are common. Looks kind of like that. So we're going to use all of these. So by hopefully the beginning of next week, we'll have all of these in our lingo. Let's see. Let's look at all right, so this is a series of anions that all differ in their amount of oxygen. All right, so ClO4, 3, 2. The one with the greatest number of oxygens, in this case, gets this ATE ending, so it's perchlorate. The one with the least oh, no, sorry. I'm reading off the wrong one. It's just called chlorite. And this one's chlorate. So the biggest one gets a per and an 8. Then we drop the per and we just call it 8. Then we drop the 8 and call it 8. And the least, ClO, is hypochlorite. Not particularly straightforward. This may be a good situation to use some flashcards. I don't usually like flashcards, but this particular table, there's not great guidelines. Like we can do the same thing right here. We had nitrite, nitrate, and phosphate. Yeah, sulfate, sulfite. So, flashcards. Sorry. Not great rules about those guys. So, which means when we're putting it together, let's do some examples. Let's see. All right, let's name these two first, and I'll come up with some other examples. All right, so when I put them together, if this was by itself, what did I just call this Mg? Magnesium cation, right? And this would be the just bromide. So putting it together, I don't have to say what the cation is. I'm just going to call this magnesium bromide. Because the bromide tells you that that's the negative one, so the other one must be the cation. All right, this one is my tricky combination one. All right, first think, where do I find copper on my periodic table? It's a metal, non-metal transition. Transition. So do I know off the bat what charge it has? No. It could be anything. How do I figure out what charge the copper has? The other half of it has what kind of charge? It's right there. Right? It's -1. So then what must the copper have to make this whole thing, right? It must be +1. So, all right, copper. Then what do I do to tell the reader that it's a +1? A little Roman numeral 1. And then chlorate. All right, what about if I had All right, so now I have Fe2 parentheses CO3 in parentheses 3. First thing, how many irons are in this compound? 2. How many carbons altogether? 3. Right, so CO3 parentheses with another 3 tells me multiply everything in the parentheses by 3. All right. So CO3, 2 minus, we call carbonate. What do I know about iron in this case? What charge must iron have to make this work out? It has to have plus 3, right? Because I have 3, 2 minuses, which altogether would be minus 6. So if I have 2 irons, I must have plus 3 of them. So how do I tell you in English? Yep, I do this. All right, let's do some in reverse. How about I give you some words, we have to try and figure out what the formula is. What about yeah, we'll do that one first. If I have iron perchlorate, I guess, let me tell you a Roman numeral. The one's usually implied, but just to be obvious, iron perchlorate. How many irons would I need in my formula then? Just 1. And then, like that. What if I had this? Now I have iron 3 perchlorate. So how many, what is the charge of the iron? All right, so I'd have Fe3 plus, and I have this guy over here. So are they 1 to 1 like this? Do I need more irons? I need more perchlorates? How many do I need? How do I tell you that I need 3 in my chemical symbols? All right, why don't we do one more? All right, so I have nickel 1 carbonate. So what charge does my nickel have? All right, +1. Carbonate's up here. So which of these guys do I need to double, the nickel or the carbonate? How do I tell you I need 2 of it? Yeah, little subscript 2. Okay. Those are just going to take some practice, getting the hang of it. All right, let me do one last thing today. We'll introduce molecular compounds and do a bunch of naming. Before I forget, there is on my website all the rules written down, how to name them with all the fancy rules, the table, and a practice page. Oh yeah, question.
Can you go back to that last slide?
Yep. So this naming ions, and there's some practice problems. If you want to do that, that's helpful, or maybe print out the rules just to have them handy. All right, last thing for today will be just introducing molecular compounds. All right, so opposed to ionic compounds, comma, molecular compounds are not as straightforward to determine what their ratios are to each other. because we can combine them in a bunch of different ways. Right, so ions, right, we know that the metals are always either +1 or +2. Or the halogens are always going to be -1. They have pretty straightforward rules. Molecular compounds don't have such great rules, but they're easier to name. So it's kind of a trade-off. Because, for example, we could make those are all 4 very common nitrogen-oxygen compounds. What law tells me that I can make these 4 different ones, and they're all good? Earlier was definite proportions. This is multiple proportions, the law of multiple proportions. All right, this is a 1-to-1, this is a 1-to-2, this is a 2-to-1, this is a 2-to-3. So all right, so that's the law of multiple proportions. It tells me I can combine them in a bunch of different ways. So if we want to talk about naming them, we're going to name the first element first. Then you're going to name the second element and put the suffix IDE on it. So if I have NO, what would you call that? Nitrogen oxide. We'll talk about on Friday. We'll do these other ones, but this one's nitrogen oxide. Sometimes monoxide, and we'll talk about how you use the appropriate prefixes to go with those suffixes. All very Englishy. All right, so we'll stop there.